Hello, and welcome to the second installment in ORNL's Invention to Innovation webinar series. My name is Dan Miller, and I'm from ORNL's Industrial Partnerships Group, and I'm going to give you a short overview of ORNL's manufacturing capabilities. Then I'm going to hand it off to my colleague, Amit Naskar, from the ORNL Carbon and Composites Group to talk to you about high-performance plastics from renewable sources. Before we begin, you should know that you can text in questions or email them at the address on your screen, ttpd@ornl.gov, at any point during this presentation. The picture you see on the screen now is an overview of the main campus of Oak Ridge National Lab. This is the largest multidisciplinary laboratory in the DOE system. The budget is approaching $1.5 billion annually, and there are about 4,400 employees working at ORNL. The thrust areas of ORNL are mainly material science, neutron science, high-performance computing, and I forgot one. But no worries, it's on the next slide. Under the signature strengths. Nuclear science and technology. How could I forget? A big part of ORNL's mission statement is in creating economic opportunity for the nation. So all the $1.5 billion that we spend on R&D annually, we are charged with transferring this technology to the commercial sector in the nation for the benefit of the nation. We have several mechanisms in which we can do this with private industry and with our industrial partners. We can do cooperative research and development agreements where we work hand in hand with our industrial partners on solving some of the most critical problems facing the nation. We can also do technology licenses where we can license our intellectual property that we have created to companies interested in commercializing the technology. We can also do work for hire, which we call work for others, in which we can do contract work for companies. And we also can work with companies that have a need to use our facility, our different facilities, through user facility agreements. And this program allows companies and our academic partners to come in and use specific facilities at little or no cost. The statistics at the bottom of the screen are our technology transfer statistics for the entire DOE system. So you can see those. And you can also notice that we do a large amount of these agreements every year. Now for an overview of ORNL's manufacturing program. Most of the manufacturing program at ORNL is encompassed under a center of excellence that we call the Manufacturing Demonstration Facility. The Manufacturing Demonstration Facility, or MDF, has several key thrust areas. The two biggest thrust areas we have are in green here, additive manufacturing and carbon fiber composites. We also have a lot of capabilities in lightweight metals processing, which include magnesium and titanium. And another technology is low-temperature material synthesis, which is a process that we use to create different kinds of high-value nanoparticles for varying applications. Transient field processing is using magnetic field processing to alter materials properties under varying conditions. And we also have quite a bit of roll-to-roll processing experience and capability. I'm going to hit on a few more of these in details before I give it over to Amit to talk about the feature portion of this webinar. Our battery manufacturing facility utilizes a lot of the roll-to-roll processing. Under this facility, we are able to create and test different battery chemistries and different parts of batteries, such as electrodes and electrolytes, separator materials, and other components of batteries, mostly for transportation applications. this facility contains several dry rooms, which are necessary to control the humidity, which is critical when manufacturing these kinds of high-performance batteries. ORNL has almost 20 years of experience in working with carbon fiber and composites. Recently, the program got a big boost when we were awarded a large Recovery Act grant in 2009 to build the carbon fiber technology facility. This facility is a 25-ton per year carbon fiber manufacturing facilities that allows us to demonstrate many of the technologies that we've been working on for the past 20 years to see if they work at a pilot manufacturing scale. These technologies include new raw materials for carbon fiber manufacturing to actually manufacture the fiber, and they also include alternative processing techniques that require a lot less energy than normal processing techniques. Also of note in our carbon fiber and composites program is the Oak Ridge Carbon Fiber Composites Consortium, in which we partner with over 50 other industrial members that are interested in developing carbon fiber composites for high volume applications. You can see more about this organization at www.cfcomposites.org. We also have a very unique set of capabilities and experiences in additive manufacturing, which you may know as 3D printing. Our experience here is mainly in developing new materials and processing techniques for 3D printing. We work with polymers as well as different metals to develop new applications, new materials, new equipment for additive manufacturing. And we have a very close relationship with many of the large 3D printing companies that currently manufacture 3D printers. And we also work with many manufacturers that are looking to take this technology and utilize it in manufacturing new complex components that can't otherwise be manufactured in any other method. You can see more about these technologies and others at the website listed on your screen. And now I'd like to introduce to you Dr. Amit Naskar, the group leader for our Carbon and Composites group, and he's going to talk to you about high-performance plastic from renewable sources.
Thank you, Dan. Thank you, everyone, for attending this webinar. I would be talking about this topic, high-performance plastics from renewable sources. Before I start, I'd like to acknowledge our sponsor for this project. This project is sponsored by ORNL's Technology Innovation Program, and also part of this work is done under ORNL's Laboratory Director's R&D fund that includes characterization of the lignin that we are using in this particular project. So before I start, the objective of this particular research is to produce commercial grade resin from lignin, and the properties of those resins should be well beyond the properties of current lignin-derived plastics. And current lignin-derived plastics are mainly some thermosets or foam type of material. And if we can make the properties equivalent to acrylonitrile butadiene styrene type resin, like ABS resin. Now, plastic materials can be of two types, thermoplastics and thermosets. We can make thermoset products from lignin, but in this particular presentation, we are not including that. That's a different kind of research. We are also doing that. But here our topic is thermoplastic materials, and these particular materials are reprocessable or remoldable and recyclable. In the screen, you will see a cartoon that says that talks about the green aspect or sustainability issues related to this project, where you can see the trees are used for making some biochemicals in a biorefinery. For example, paper or pulp, or even cellulosic biofuel, or some other plastic like polyamides from tall oil type products. And then all those biorefineries are producing co-product lignin, which is almost 15 to 35% of the dry mass fraction of biomass, and those are currently being burned. And then this can be utilized in this way to make some bioplastic. Now, here in this cartoon, I'm showing that these bioplastics can be induced to biodegradability, although we are not doing that work at this moment. Some work is going on in different sectors, and we can talk about that later on. So that's our theme. Let us first talk about the status quo. So where are currently lignin is used? First of all, plastic type materials, it consumes almost like 4% of global petroleum usage, and also 25% of petrochemicals if you talk about petrochemical materials. Now, lignin is biomass derived product, as we talked about in previous slide, and this is used for making, for example, plywood product. It can be used as binder in ink, or even some foam. In fact, some automotive industries are using lignin polyurethane foam for car seat and other porous materials application. Now, this is the current use of lignin, and we want to talk about some aspects of styrenic polymer versus lignin-derived copolymers. Styrenic copolymers, those are petroleum-derived material, and you can find that today's issues related to styrene, that VOC or volatile organic compounds come out during styrenic polymeric materials, and industries are under monitoring of VOCs. So they would prefer green aspect if someone can replace styrenic materials with some other materials. So here, our objective is to replace styrenic materials with lignin. So let us first talk about, and some of you might have seen this slide before during Oak Ridge Carbon Fiber Consortium's last meeting during fall or spring. This is a rheometer data, rheological data. So different types of lignins were isolated from popular genotypes that were grown in ORNL. Our researchers at Bioenergy Science Technology Center, they are working on genotypes of different kinds of bioproducts from biomasses. So they are growing these trees, and we isolated at least 5 or 6 different types of trees, popular trees, and we isolated the lignin under identical condition. And when we did the shear rheological study, and I'll come back to that later on, why we are doing rheology, then you find that the viscosity of the melt, lignin melt, differs by a couple of orders of magnitude, although those are all from hardwood poplar lignin. So all lignins are not same, and if we can understand the chemistry of lignin, we can tailor the product, and that's the message here. The reason we are doing rheology here, because we are talking about thermoplastic, those needs to be processed under shear condition for molding or part manufacturing. So rheology is very important. And so here we are seeing different lignin will have different reactivity and different kind of viscosity history. Now, how will it work? Of course, lignin itself, as some of the lignin, let me go back to previous slide and talk about some of these are hardwood lignin. And if we do softwood lignin, in fact, you will see that those will not flow, and the viscosity will go at least 4 or 5 orders of magnitude higher, and that would stop the rheometer. So how that different kinds of lignin would work to make different kinds of thermoplastic. Of course, we have to add some other additive. And those additives can be like functional additive. There can be a covalent bonding between those additive and the lignin, or there can be just physical interaction, and we can make the thermoplastic product. Now, in this particular technology, whatever we are talking about, we don't need extensive lignin purification. The reason for that is we are not preparing a carbon precursor or some other specialty or fiber forming material at this stage. So inorganics that are present in lignin can stay there as it is, as long as it is not very high in volume percentage. So as received lignin from industries that are commercially available can be used to make this kind of product. And in fact, in some thermoplastic materials, for example, polypropylene, people use some inorganic chemicals, for example, calcium carbonate, for controlling the crystallization kinetics. So these lignins can be used to make with additives thermoplastic product by appropriate processing condition. And in this case, again, we are not relying on chemical synthesis or lignin modification aspect. We will just use as received lignin and reactively extrude it to make the desired product. Of course, different kinds of lignin will have different properties. For example, hardwood, softwood, or annual fiber-derived lignin. And that structure property processing relationship we are currently exploring. Now, let me switch the gear. Let me talk about thermoplastic elastomeric material. On the screen, right-hand side, you can see a cartoon here that shows a polystyrene domain and some soft segment. So these are the styrenic block copolymer structure in cartoon form. So polystyrene domains are the hard phase and soft segments are shown as flexible line, and several polystyrene domains exist there. And you may want to pay attention to the scale bar here, which shows 1000 angstrom or 1 nanometer scale. So that means these hard and soft segments are well dispersed in domain form within a nanometer scale. Now, question is, can we create that kind of homogeneous structure replacing this polystyrene with lignin? And for that kind of approach, we do not necessarily rely on copolymer synthesis approach here. So that requires synthesis using different setup, and again, isolation of the polymer or purification of the polymer, precipitation, and all those unit operations can be eliminated if we use a path that involves blending of hard and soft phases. And this is something that I learned during my graduate studies, that rubber and plastic can be blended in presence of some cross-linker to produce thermoplastic elastomeric materials, and this rubber is the soft phase and plastic is the hard phase. In this case, we are talking about the plastic is being lignin. Now, let us go back to our previous studies and why we are doing this. First of all, we did some preliminary work and we published and filed patents that are related to utilization of tailored lignin. We first did lignin modification by cross-linking to control the molecular weight and also to control the lignin glass transition temperature. And then again, we coupled it with different soft segments, telecalic polybutadiene, for example, here in this case. And you can see with increase in lignin content, here, of course, our lignin content was low, only 37%. You can see the product, block copolymeric product, that flows near 25 degrees Celsius. So it was, it proved the concept, but it was not a great product. We published that, and then we also produced polyurethane chemistry by utilizing rubber diisocyanate. Their lignin can be coupled with diisocyanates to form polyurethane. It's a very straightforward chemistry. In absence of moisture, it can give great yield, unlike polyester. And you can see the dynamic mechanical property got significantly improved. Now, in previous case, it was flowing near, modulus was dropping near 50 or room temperature. Here now it is flowing near 150 degrees Celsius. In some cases, it doesn't even demonstrate that flow characteristics. So we made significant improvement by doing the chemistry before we started this particular project. And based on this background, we learned that lignin can be modified to value-added thermoplastic by copolymerization approach. Now, our current approach is, can we now demonstrate that using reactive processing technique? So in this case, of course, we used an extruder to modify this lignin. And in the screen, you would see a dynamic mechanical analysis data. The dotted line shows a rubber phase blended with lignin. And you can see the identity of rubber phase and lignin phase are clearly visible there. The lignin has a softening point near 150 degrees Celsius, and rubber has a softening point below minus 50 degrees Celsius. So then this particular product did not show a great mechanical property. It was less than 2 megapascal. Then we did the interfacial adhesion of those two phases by tailoring the chemistry. And once that was done, then we saw a significant jump in the mechanical properties, 6 megapascal tensile strength in that material. And you can see now the rubber softening point is close to 0 degrees Celsius, and lignin softening point got closer to the rubber one. So there is a great improvement in compatibility in the blend, and that was the reason for improved performance. And we exploited that, and in fact, we filed a patent application on this particular concept. Then our focus remained, now can we further improve the mechanical properties beyond 6 megapascal? So we did several formulations, and the tensile stress strain plots are shown here in this on the left part. You would see, so this is the red curve. That was the material almost like 6 megapascal tensile strength we were talking about. Now, unfortunately, here I'm showing the tensile stress in KSI, industrial unit, not in SI unit. So 1 is equivalent to nearly 7 megapascal. So we tailored the different formulations here. As you can see, we added some other additive, and then we are seeing the deformation curve, tensile deformation curve is changing significantly from rubbery to, in fact, some plastic deformation, yield stress, you can see. And this is a very encouraging result. We improved the mechanical properties almost 3.5 times and showing some yield stress. And based on that, we learned a lot, and we are further working on it. Now, as you can see, this is a group of lignin that work that way. Now, when we applied the same chemistry on another group of lignin, we don't see that kind of improvement in mechanical property. Rather, some of these additives reduced the mechanical property, and the material became again rubbery. So our additive is almost like a plasticizer for some lignin, and for some lignin that is a strength enhancer. So that's where we believe lignin structure and properties are contributing to the mechanical property, and that gives some new product that has sometimes yield stress. Now let us look at the properties again in case of where it is showing the plasticizing effect, which is obvious. So neat lignin is shown in the green curve, and when we are adding moderate loading of plasticizer, then it is dropped because of the softening effect. And then further addition, again it lowers the mechanical property, but it shows a little bit of yield stress, which is not that significant. Now when we did that for another group of lignin, as I talked earlier, you can see that it improved, and in fact it induces a great deal of yield stress and ductility in that material, although it is not that ductile, and we are currently working on it. It shows only 15% ultimate elongation. But the material is tougher than the previous weak lignin-based material. So based on that, I would like to come back to our quantitative impact. What was our goal and where we stand on this particular project? We are assuming here all these formulations have more than 50% constituents of lignin, which is a plus point. So we can say that this is a partially carbon neutral product. And these biothermoplastic compositions with lignin, we are assuming the cost can be 30 cents per pound, since we are not seeking highly purified lignin. And our target was, can we make lignin-based thermoplastic greater than 10 MPa and more than 100% elongation? So this is almost like a thermoplastic elastomeric material. And of course, at the end, we have to demonstrate composite part with greater than 10% elongation. That would be a tough product, and that is a very tough goal too, and we are currently working on that. So if you look at commercial lignin-based plastic, polyurethane and other foams, they produce very weak, brittle, porous material, and those are very low in mechanical property. For example, 3 megapascal tensile strength and even less than 10% ultimate elongation. So our goal was to get 10 megapascal strength and 100% elongation. And I'll show you some of the results later on in the summary slide. As you have seen here, some of the products have 100% elongation, and the mechanical properties are close to 15 megapascal. And some products are even 20 megapascal. I have not shown those results here. Now, let us look at the competitive differentiation between this particular product versus other engineered thermoplastic that are commercially available. So we categorized the technology feature in different aspects. For example, low-cost feedstock. This particular technology, ORNL technology, it is indeed a low-cost feedstock. It takes lignin and other lignin-derived resins, of course, that has similar competitive advantage. But petroleum-derived resins, those require high-purity monomer for synthesis of those materials, and those are not low-cost feedstock as such. Purity requirement, as I mentioned earlier, our reactivity is based on a particular functional group, and this is not a polymerization reaction truly that we are conducting in this particular set of polymeric material synthesis by extrusion process. So it doesn't care about that much, that stringent purity requirement. Of course, petroleum-derived resin or other engineered thermoplastic that requires pure monomer to synthesize that material. Processing cost is easy because we are utilizing simple extrusion technique and other lignin-derived resin that requires one-part synthesis and then again purification, further processing, and of course that is common for other resins too. Toughness, yes, of course, our material, as you have seen, it is in some of these plastics, it is better than ABS resin. ABS resin elongates only 5%. Our products are all more than 20% elongation, and some elastomeric material, in fact, are elongating 400%. And toughness-wise, of course, some petroleum resin are competitive that way because those are coming from high purity monomer, and those are tough engineered plastic, but those are not carbon neutral. In terms of carbon neutral aspect, yes, we are. So it is partially green or in between of green and red. We say it because we are using 50% lignin in this composition. Of course, another drawback in this material is if we use craft lignin, then it is not odor free. So it smells bad because of presence of sulfide or mercaptan group. However, we can use a different kind of lignin for that matter, which is not particularly a craft lignin. It could be organosolv or even soda pulp lignin that doesn't have sulfur present in it, but it would smell like woody product. So that is advantageous for petroleum-derived product. Of course, another drawback for this material is it is not transparent because lignin is a colored product. So you will see these materials are colored in nature. So let us now look at the target customers for this particular technology. As we are talking about, this is a resin equivalent to ABS resin, so it can be used for automotive structural part manufacturing. And in fact, we are interested. We talked at some point, some of the researchers in these companies. Of course, it can be used as resin additive or resin modifier. For example, phenol formaldehyde resin, that is lignin can be used that. But we are not necessarily talking about those kind of thermoset resin. So these polymer that we are synthesizing or producing that can be used as additive in other material. In fact, we have demonstrated that this material under certain condition can replace almost, not only this material, only lignin itself can replace almost 40% of ABS resin under certain compatibility condition. So our different customer may find interest in that particular aspect of our technology. Of course, it can be used as additive for making manufacturing foam, like people do for polyurethane or other foam. There are several plastic material, for example, low-density polyethylene and other material that can be foamed, and we are currently working on making foamed product from this particular thermoplastic material, and we believe several petroleum refinery-based companies would be interested on this particular technology. Now let us look at the market price, market opportunity of this particular product. So my colleague Dan, he found these data from published articles or reports. As you can see, thermoplastic resin has high volume usage this is particularly for global composite industries, not necessarily automotive, but thermoplastic resin has high consumption, high volume of consumption, almost second to polyester. And the cost of this material is slightly above $1 per pound. Now, if we look at our product will be well below $1 per pound, and since it has a carbon neutral feature with it, so it has a competitive advantage. Now, with that, I would like to summarize. So we have learned a lot through our previous practice on lignin-derived product manufacturing in ORNL. Either it is carbon fiber-related project or resin-derived project, resin synthesis project, and ORNL made significant investment on this particular technology, and we learned and we are leveraging those knowledge base to develop new products. This current product is at technology readiness level 5. We have demonstrated that this material can compete with ABS resin type. And so far we have demonstrated 30 megapascal tensile strength with 30% ultimate elongation. ABS may have 35 megapascal and 5% ultimate elongation. Also, some product can be categorized as halfway through that, 18 megapascal tensile strength, but 100% ultimate elongation. Some materials are a little soft or rubbery. It would be 8 megapascal tensile strength and 400% ultimate elongation. So we can categorize, depending on the selection of lignin or additive, we can categorize different products. I would say that top one would be engineering plastics equivalent, and bottom one would be almost like rubbery products, materials. Now, major focus will be to market this product against petroleum-derived plastics, and that's what we will encounter in our next step in this particular research. And also, our intellectual properties are ready for licensing. We recently got awarded with a US patent that was issued June 10. It was not yet published. I just received a letter. And US patent application has been lately filed and another invention disclosure made. And you can see the different molded products that we made, one with this oak leaf embossed article. So I would like to acknowledge again our sponsor, UT Battle LLC, through Technology Innovation Program, and our ORNL's Partnership Directorate for their support on this project. We also acknowledge Laboratory Directors R&D Fund for lignin-related work for lignin characterization. And of course, my colleagues, many of my colleagues contributed to this work. Josh Parkins, who just left ORNL, Jim Cron, he's working with us, Sam Akato, a postmaster's candidate, Tony Bova, a PhD student, and Mark Goldman, an undergraduate student. So, and again, contact information for me, it is 865-576-0309, my phone number, and my email address is given there. So this is our next schedule of webinar. Our next webinar on July 16th on cast alumina forming stainless steel. And the other in this series are shown here in this particular table. It would be almost every 15 days, bi-weekly. All other technologies will be displayed there, and I'll be happy to answer any questions.
Thank you. We do have a few questions that have been texted in. The first one is, what is the current cost of material to be replaced by 30 cent per pound lignin?
What is
the current cost of the material available that would be replaced by 30 cents per pound lignin?
So it would be again less than $1 per pound. Of course, if you can do the math right now. For example, if ABS is $1 or 20 cents per pound, I don't know current price of ABS, maybe close to $1 per pound, and you can think about 30 cents per pound of lignin, and we have demonstrated that you can add 30% of that with little additive, 30% of lignin. So I believe you can replace at least 40 volume percent of ABS, which is $1 per pound, with 30 cents per pound. So it would be just, you can do the math. It would be almost like 70 cents per pound.
Thank you. Another question. Thank you. Another question has come in. The question is, are these plastics biodegradable?
So as I mentioned in my probably second slide, that some folks in our lab and outside, they're working on it. We can induce biodegradability, but not all of our additives would be biodegradable. We can choose some of those, but that is not at this moment our focus, but we can work on that if a particular sponsor is interested on that aspect. We can certainly, lignin can be made to biodegradable, and that's the kind of work other folks are working on. We probably can do that, but it will not be 100% biodegradable. For that, we have to select biodegradable matrix as additive. And I cannot talk much about that at this moment. We are currently working on that.
Another question is, what are the main steps that would need to be taken to commercialize this technology?
Well, so to commercialize, as I have mentioned, that it is right now at technology readiness level 5. So something needs to be commercialized. It needs to be upgraded to at least 7 or 8 level. So we need to demonstrate. Just now we have made a plug, molded plug item, but we need to make a part. Either it is automotive part or maybe car window channel or something. Some sort of part we need to demonstrate with our industrial partner or whoever would be interested in this technology. And then as long as we have so far produced a couple of pounds of material by extrusion technique, and if we can make continuous processing, we have to demonstrate that. As soon as we can demonstrate that, it is ready for commercialization. Property-wise, it is great, no doubt.
And I think we have time for one more question. You mentioned that the plastics are recyclable. Can you elaborate on this process?
Well, so this particular polymer is recyclable. That means it is not thermoset. You can remold it. But if we use continuous carbon fiber reinforced composite, then recyclability will be a different challenge, because how will you, if it is continuous carbon fiber, but if it is a chopped fiber reinforced resin, that if you use, anyway, these plastics will be used if it is used for structural application. Either glass fiber or carbon fiber will be used to reinforce it further. If it is chopped fiber reinforced composite, then it can be remolded, and we know that what are the additives can do the plasticization on this material, and we can probably shred it and mold it again. So it can be recyclable.
Thank you.
So thank you all for attending the webinar, and we'll be staying in touch with you. If you have any question, please contact us and wait for the next webinar. Thank you.